Thank you. So I'm going to talk about approximately counting graph homomorphisms, as you can see. It's joint work with Andreas Galanis and Mark Jerem, who are around here somewhere. And Andreas gets extra credit for drawing the pictures, which you'll see it would be impossible to explain without. So the slides, yeah. And some of the things that I'll mention have been in the boot camp, and if you weren't at the boot camp, or even if you were, please stop me. And if anything's unclear, I'd rather explain it, so feel free to interrupt any time. Okay, so graph homomorphisms. So I'm going to call them H colorings, as they're sometimes called. So let me start by just telling you what one is, so we're reminding you. So an H coloring, or a graph homomorphism, is a map from a graph G to another graph H, which I'm going to call the template just to avoid confusion. And all it is it's a map from the vertices of G to the vertices of H. And it has to have one property, which is that edges have to map to edges. Okay, so I've drawn a picture here. Here's our graph G, and I've drawn a map from the vertices of G to the vertices of H. So that guy got red, that guy got blue, that guy got green, etc. And this map that I drew is a homomorphism because red's allowed to be adjacent to blue, and blue to itself and blue to green. There's no red next to red in this picture, otherwise it wouldn't be a homomorphism. Okay, so the rest of the talk is about that. So I would pause. Is that clear? Okay, so that's what a graph homomorphism, or H coloring, is. Sometimes we refer to the nodes of H as colors, so I might do that. All right, so lots of combinatorial problems can be represented as graph homomorphisms, or H colorings. So for example, if I took H to be this little graph here, with two vertices and one self-loop, then homomorphisms to this H are independent sets. Because I could think of red as being in the independent set and blue as being out. If I take a map from the vertices of G to red and blue, but I don't have in next to in, it's an independent set. Okay, and I guess the other classic example, if I take a clique, for example, a clique of size 3, then homomorphisms from a graph G to a clique are proper 3 colorings, because this H has all edges except for self-loops. So I can color red, green, blue however I like, provided I don't put a color next to itself. Okay, so by varying the template H, we vary the problem. That guy was independent sets, that guy was colorings, and of course we could take any H we like. Okay, so that's what a H coloring is. Now I'm going to talk about, so this workshop should be about the classification program and complexity. So I'm going to start by giving you a little survey about algorithmic problems to do with H colorings. So I'm going to start with the H coloring decision problem. And Hel and Nessatril both here, this work really kind of initiated this area. And the question that they studied was, suppose you fix a template H. Okay, so just fix that. And now, what if I have an input graph G? That's the input. And the question is, does G have an H coloring? Okay, so what they showed is that this problem is in P, if H has a loop, or if it's bipartite. But for every other single fixed H that you could consider, the problems then be complete. Okay, so let's think through this. The NP is the easy direction, so let's do that. That's easy, okay? So let's look at an H with a loop. Suppose I take an input G and I want to say, does G have a homomorphism to this H? The answer is yes, right? Because you could just map everything to blue. It's got a loop, so all edges are mapped to edges. Is that obvious? So that's easy. The other thing that's easy is that it's in P if H is bipartite. So let me talk you through that. Suppose I have a bipartite graph H, and I want to check whether there's a homomorphism from some input G to H. Well, first, if G has an odd cycle, then the answer is no, because how could you put an odd cycle into a bipartite graph? There's nowhere for it to go. Okay? So now let's suppose I have a graph G that's bipartite. Let's assume for a minute that it's connected. How many homomorphisms are there to H? Well, one side of G could go to this side of H, the other side could go to the other side, and then you're home free. Yeah. So, I'm sorry, I'm not doing counting. I got ahead of myself. We're trying to do decision, so map it to an edge. Okay, if it's bipartite, map it to an edge, and you're good. Okay, so those are both easy. And what was really great about their work was not that, but the fact that they managed to show that for every single other H, it's NP complete. So it's just comprehensive, every other H, that's it. So we completely understand all H. These are easy, everything else hard. Okay, and so that was a substantial effort, and I'm not going to tell you how to do the hard bit. Okay, now this is what I started jumping into accidentally. What if we're interested in not decision, but counting graph homomorphisms? And again, this has been thoroughly studied by Dyer and Greenhill. And here's the theorem that they gave. The question is, input graph G, how many H colorings are there? So again, we fixed it, so that's a parameter of the problem. We want to know, if you're given an input graph G, how many homomorphisms from G to H? Okay, so what did they show? First of all, let's suppose that the H is a clique with all loops. So every edge that could be there is there. Okay? Now, for a minute, I want to consider counting homomorphisms from a connected graph G to this. What's the answer? Well, if G has n vertices, then it's 3 to the n. Right? You can just do anything, because all the edges are there. Okay. The other easy bit, what if H is a complete bipartite graph? What if G is connected? And I'm going to get back to the connectivity thing in a minute. How many homomorphisms are there from G to H? Well, if G has an odd cycle, 0. We can't go anywhere. What if it doesn't have an odd cycle? This is the bit I was jumping to before. Well, what can you do? It's bipartite. Put one side of G to one side, the other to the other, and now you can do everything. Okay, just a multiply out. Okay, now, what they show, those are the two easy cases. Now let's think for a minute, what if G's not connected? Okay, well, if you wanted to count homomorphisms from G to H, what would you do? You'd take each connected component of G, count homomorphisms to H, and then multiply them, yeah? So that's what you do if if H is connected. What if H is not connected? You would add, right? If I wanted to do homomorphisms from G to a graph that has this component and that one, G is connected, send it here, send it there, add. Okay, so connectivity is no issue for us in this easy direction. And so the easy part of the theorem is that every connected component, if it's a clique with all loops or a complete bipartite graph, then this is easy. And again, the deep part of their theorem is that if H even has a component that doesn't look like this, then it's actually number P complete. Okay, so I want to pause because I think I maybe was quite clear. Are there any? Is that good?
What's FP?
Okay, excellent. So please ask all such questions. So FP just means what you can compute in polynomial time, but it's. You want to? Go ahead. Okay, so FP is whatever you can do in polynomial time, but it's not a decision problem. The output's a number, so that's why it's called FP. Any more things I forgot to explain? Okay, so that's there. Now, often many people here work on actually approximately.
So why was the singleton appeared?
The singleton was there because this is a complete bipartite graph with no loops.
Okay.
And I just wanted to make the point that this should be counted in those things.
And are you going to give us an idea of the hardness result? Or?
I'm going to give you an idea about approximate hardness, and if you, that'll give you some idea, and then if you want to talk about exact, we should probably do it after, but yeah. But you're right, so far I'm telling you the stuff that you could figure out in 5 minutes and not the deep stuff that's hard, but okay. Okay. So what about approximate counting? So, as people who've been here a while, and even people who haven't probably know that one of the kind of standards for success in approximate counting is the F-praz, so that's the notion that I'm going to use. So again, the question is going to be fix H, the template, input a graph G, and now also input an accuracy parameter, if I can say it. And what you want to do is you want to output a number which is, with high probability, quite close to the number of H colorings. How close? Well, it should be, the parameter epsilon controls how close, and as epsilon gets smaller, it should get closer. The running time is bounded by a polynomial in V and 1 over epsilon. Okay, so that's what we're going to use. I think when Dick introduced this, you 1 plus or minus epsilon, but it's the same thing. So I just wrote it this way so that I could, yeah. Okay? All right. So that's the question we're going to talk about next. How hard is it to approximately count H colorings? And as a warm-up, I put up 3 vertex H's, and like Dominic Welsh always used to do, I've color-coded them. And I'm going to use this slide as a way to introduce some ideas that I think a lot of people know, and then we'll move on. So these are 3 vertex connected graphs H. I've drawn all non-isomorphic ones. And the question is, how hard is it to approximately count H colorings? Okay, so the first thing I'll draw your attention to is the green ones. Okay, you can see. This is easy because it's easy to count exactly, right? We just saw that. Same thing. This is a complete bipartite graph. So we know it's easy to count homomorphisms to that. So those guys are easy. All right? And the next thing I want to do is I want to glance at all the red ones. And the red ones have the property that it's NP hard to approximately count graph homomorphisms. And what I'm not going to define formally in this talk, because it's not very important, but I'm not going to define the notion of approximation preserving reductions. But basically an approximation preserving reduction between 2 counting problems has exactly the property you expect, that if you can F-praz one, you can F-praz the other. Okay, so it means they're sort of equivalent. And these red guys are equivalent to counting satisfying assignments. And what's known is that's actually as hard to approximately count as anything in number P. So some of this we've done before in the boot count. And that means that if you could approximately count, you would know that NP is equal to RP. So those guys are really as hard as can be within the class number P. And I'm going to take questions on this because I think this is kind of a background slide without stating stuff. But let me draw your attention to this blue guy. So there's one odd one out there in this picture. And this blue guy is exactly as difficult to approximately count as counting independent sets in bipartite graphs. So if you hear, you probably think, yeah, you've heard a million talks about that. Otherwise, it might seem a little strange. But the point about counting independent sets in bipartite graphs is that it's equivalent in difficulty of approximation as loads of other problems. And it's complete in this logically defined class, which I won't define, RH pi 1. And it's kind of believed to be of intermediate difficulty. So we don't really believe there's an F-praz for that, but neither do we really believe it's as hard as the red guys. But this is a classification program, and what's going on with these 3 vertex graphs is that we understand all of them. These guys are easy. This one is complete for this intermediate class. It's exactly in difficulty of counting independent sets in a bipartite graph, which is the canonical problem for that class. These guys are all equivalent to counting satisfying assignments, which is the hardest you can be in number P. Okay, but not everybody was here for the boot camp, so are there any queries about that That's the kind of basic framework that we're going to work in. And I haven't told you anything about H's that have more than 3 vertices yet. Is that good? Okay, so that's the vertex H, and I guess this classification was known quite a long time ago. And the truth is, despite that, we still don't know everything there is to know about all H. So as the talk goes on, you'll see that there are going to be some things we know, but we don't have a beautiful classification for all H, such as the ones that I showed you for decision and for the exact counting. So I'll show you what we do know, but it's less than everything. Okay. Okay, so here we go. We don't have a trichotomy for all connected H. And I thought before I go on to what we know, I'd give you an example of what we don't know, because it's so simple. There are even 4 vertex graphs whose complexity we don't understand. So 3, we knew everything, but if you just go up to 4, we've already got open problems, believe it or not. And here's an example of a graph that we don't know its complexity. So we do know that this is as hard as BIS, as counting independent sets of bipartite graphs. But we don't know whether it's as hard as SAT. So it may live in between, for all we know. And there are other such problems, and Stephen Kelk's thesis has a whole bunch of them. This particular problem is interesting because it's equivalent to counting 4 colorings in bipartite graphs if your input is bipartite. And so counting colorings of bipartite graphs is some class of problems that may live between BIS and SAT. We don't really know. But that's quite interesting. So I just want to draw your attention to that as something that's not understood.
Just, what's the evidence that BIS is really intermediate? Is it really strong, or is it just...
No, it's not really strong. It's never very strong.
No, I mean, sharp set is not, going to be...
Yeah, so the question, in case we do, the question is what's the evidence that the BIS is intermediate? And I wouldn't say that there's very strong evidence. So one thing that happens with BIS is that problems have a feeling about them. This is getting really vague, but let me do it anyway. It's kind of a parody-like feeling. They have a feel, which you can spot, and quite a lot of problems that are really apparently different turn out to be equivalent. Like the one that I think is the most strange is counting stable matchings, for example. So the evidence is that there are a lot of problems that turn out to be equivalent, and they feel a little bit different. But we don't have good. I mean, they could all be hard, and we're just too stupid. Yeah, I don't know. Or they could all be irrepressible. So could envy, but yeah. Okay. Okay, good question. So what I'm going to tell you about in this talk is something Mark likes to call no life below BIS, so I put that on the slide for him. Anyway, it's about whether there can be things that are easier than BIS, but for which we don't know if prezes. So that's going to be the goal of this. So I'll spoil the punchline by telling you that what we proved in this work is that there are no H's, apart from the trivial ones, that are easier than BIS. Everything's at least BIS hard. So I'm going to get there. But before I get there, I'm going to take a detour into the complexity of sampling. And the reason for that is that it's easier. And I'm going to tell you about some much older work that we did on sampling, and then I'm going to talk about the problems with moving that to counting and how some work of Lovesh's, which was always there, we just didn't know about it, is the missing ingredient that helps fill in the picture for counting. Okay, so I want to talk briefly about sampling, and you'll see why. And I don't want to do it very formally, but a polynomial approximate sampler, we do need to know roughly what that is for sampling H colorings. So the input's going to be a graph and an accuracy parameter, again, epsilon. And the output is now going to be a random H coloring drawn from some distribution. And the point should just be, it doesn't really matter exactly what distribution the outputs are from, but the total variation distance between the output distribution and the uniform distribution on H coloring should be small. So you can output from any distribution as long as it's close in total variation to uniform. And the runtime can depend on the number of vertices in epsilon, and we could make this a fully polynomial approximation scheme by demanding that you spend a little less time with the accuracy parameter. I don't want to spend very long on it because that's not very important. The important thing is the idea. You're just sampling H colorings from a distribution close to uniform. Okay, so we have an old theorem, which I want to talk about a little bit, which says if you take any graph H, which is fixed as usual, and doesn't have any trivial components, okay, then if you could sample from close to the uniform distribution, so if you could pick an H coloring nearly uniformly at random, then you could F prize bis. Okay, so that's kind of a bis hardness, but note, sorry, that's not, no. Okay, so you could F prize bis, so obviously you could F prize everything in that class R8 pi at 1. But the thing I expect, okay, who knows. What I wanted to say about this is it doesn't tell you about approximate counting. So normally with self-reducibility, for self-reducible problems, we think of approximate counting. We know that approximate counting and sampling are basically of the same difficulty, and that's true. That goes back to Jerem, Valiant, and Vazirani. But here, we have a result that says, if you could sample H colorings, then you could sample independent sets in a bipartite graph. That's self-reducible, so you could approximately count independent sets in a bipartite graph, hence you could do everything in that BIS class. So it's a weaker result. It just shows hardness for sampling, doesn't tell you anything about approximate counting. And I'm going to talk a little bit more about why this is easier to prove, and then a little bit we'll come back to counting. Okay?
Could you go back to the last slide for a second?
Yeah.
So I'm just trying to understand what the sampling is kind of outside of this was this.
Sure. And let me, so the intuition is probably more important than the details. So the intuition should be, the input is G, the output is an H coloring of G, and the distribution from which your algorithm chooses the output should be close to uniform, but it doesn't have to be perfect. And there's some accuracy, but it doesn't really matter exactly what the details are. Yeah?
So you're trying to measure how difficult it is to do this?
Yes, exactly. So this is a computational problem because I've got the input G and the accuracy parameter. And then what I want to know is there a polynomial time algorithm? Obviously, it ought to be a randomized polynomial time algorithm.
Okay, now I got it.
Perfect, thanks. And thank you, and please, feel free. That's good. Okay. Okay. So I want to make one remark before going on, is that when we get to approximate counting, actually whether the thing is connected or not makes a difference. So I told you for Dyer-Greenhill's result that they had the very strong result that if you have any hard component, then the whole problem becomes hard. That's not true for sampling, and maybe just ignore the words, but look at this picture. And all I wanted to draw your attention to is that the graph H that consists of both of these components is one for which it's actually easy to approximately count H colorings. And I don't want you to compute the technical details because they don't matter, but here's the point. Suppose I was faced with this H, and I wanted to pick a random or approximately count H colorings. Here's what I'd do. I'd say, what is my given accuracy parameter? Is it really, really small? If it's really, really small, I have a lot of time. And I have so much time that I just count the independent sets of the graph, so I know how many, and then I know what 3 to the n is, and I pick one randomly. Okay, what if epsilon is not so small, so I don't have much time? Then I just ignore this component, and I just pick a random homomorphism from my graph to here. And the data goes on and boom, but it's good enough, it works, okay? So you get an approximate counter out of that. So unlike the case for exact counting, we do have to worry about components, and what I'm going to tell you for the rest of this talk is going to be about connected for that reason. Okay. All right. So I said that. Okay. Okay, so I do want to make one more point here. So I talked about the fact that for self-reducible problems, approximate sampling and approximate counting are the same. We do know from a paper from a long time ago that there are technical problems where they aren't the same. So we have a paper from a long time ago that showed that if you could approximately sample H colorings, then you could approximately count them. So we know one direction. The other direction we don't know, But this paper did give a little artificial example, including discrete log, it doesn't really matter what it was, to show that you can't always go the other way. So there was a little problem in number p, which, subject to some complexity theory assumptions, you can approximately count but not sample. So that we have to consider the possibility that they're not always of the same complexity. Okay, so that's just a heads up.
Could you define recent since 2004 is a long time ago for some of us, perhaps in the room. I'm sort of just making a joke. I mean, you keep saying a long time ago for 2004.
Okay, yeah, well...
So what's recent?
What's recent? I don't know. Recent is, these guys that haven't made... I don't know. I better not try. Okay. Recently, we showed. Yeah. All right. So, all right. Yeah. All right, so the questions that motivated the current work, which is more recent, we wanted to know, is there a graph for which approximately counting is actually easier than approximately sampling? And also whether there's a graph that lies between P and BIS. And it turns out, in this case, we found there's not, so I'll tell you a bit about that. In this case, there still could be, if BIS and SAT are different, one up there, we don't know. Okay. So finally, the theorem that I was going to tell you about now, which is with Andreas and Mark. Okay, so that's what it is, what I've been talking about. So let H be a graph. We always have self-loops, possibly parallel edges. It's not very interesting, but we don't have them. Connected components need to be non-trivial, otherwise we don't know. So there's an open problem. And what we show is that approximately counting H colorings is always at least as hard as this. So we're not going to formally define the reducibility, but what we're going to show is that if you could approximately count H colorings, you can indeed. Okay, so, and the key technique is going to be, that's going to enable us to do it in the counting world, is to show that gadgets exist using kind of non-constructive tools due to Lotze-Lovash. So we're not always going to have the gadgets that we need to hand, but rather we're going to sort of show that they exist. So that's, okay. So let me start with a very high-level proof overview. And then I'm going to kind of veer into showing how to do some of it in sampling, which is a little bit easier, and then come back and show how the stuff with Lotze really is really very useful. Okay, so what if we wanted to show that for every non-trivial H, that counting approximately H colorings is this hard? So obviously you've got to handle all H's somehow or other, so a natural way to do it is by induction. So we know how to handle 2 vertex H's, so that's nice. So base case 03 or whatever, base cases are pretty good. So for the inductive step, what we'd love to do, what anybody might try, is we might like to find, given a graph H, some smaller graph H primed, which itself has no trivial components, so that we can inductively handle it. And then we just want to prove that H prime colorings reduces to H coloring, right? If we could carry out this scheme, that would be a good scheme, right? So we know for all 2 vertex graphs that all non-trivial ones are BIS hard, because indeed there's not many 2 vertex graphs, and the only non-trivial one is the independent set. And so the idea is, just given any H, we want to identify a smaller H which doesn't have any trivial components, so that we can deal with it and reduces to H. Okay, sounds like a good plan. And so of course the main task is figuring out, given a graph H, how to find such an H prime. So that's what I'm going to talk to you about. Okay, so like many of the slides, I think there was a talk the other day that had a first attempt. I can't remember whose it was. Anyway, here's a first attempt. So let me show you how you might find such an H, and this will give a hint on how it's done and how it's not done and all sorts of things. So let's say that we want to find such an H. Well, I'm going to just work by example. So here's H. Might look a little exotic, but I want enough room to illustrate a few things. This H is rather easy for me, though not easy enough, because it has a unique vertex of maximum degree. So I'm going to illustrate some things using this H. What if I wanted to show that this H was hard by just doing the inductive step? Okay. Well, this vertex here has a unique vertex of maximum degree, and so I want to think about how I can use that. Okay, and then what I'm going to do is I'm going to identify, I think I didn't say it, I'm going to let V star be this unique guy. I'm going to let H star be the graph induced by its neighborhood. So I hope you can see the colors. It's in red here. So there's this path of length 3, and then there's this thing here. That's induced by the neighborhood of my guy. And, well, okay, it's smaller and it has no trivial components. And what I'm going to try and show you is that, indeed, H star reduces to H. So we're working towards this very elementary inductive scheme. Okay? And here's how you would do it. Okay, so this is a quite nice one. So here's how you might do it. Suppose I wanted to show that H star colorings reduces to H colorings. Well, all I would do is I would take some input to H star colorings, would take a huge independent set, and I would construct a graph like this. Okay, so I think this is hopefully quite easy to see. Now, what would happen if I approximately counted H colorings of this graph? Well, this independent set is huge. So in a typical H coloring, this vertex W would have to get colored V star, right? Because it's the unique vertex of max degree, and that gives you the most entropy here. Okay? Is that... Okay, so I want to, because I'm going to move on, let me just, I saw a few screens that maybe look like I didn't explain that very well. Okay, so I've got a graph H, and what we're trying to do is this inductive scheme. Okay, so what we're trying to do is pick out a graph H prime, which may be a subgraph, and it should have no trivial components, and it should be smaller. Okay? And that's because by induction, we'd show that counting H prime colorings is biz hard. And so the only bit I want to do is show that reducing H prime colorings reduces to H colorings. Did that work? Everyone, there's no point losing it. Yeah? Is that good? Okay. Then, for this graph here, which is just an example I wanted to show you, it's quite easy. So I want to show you that it's easy for this graph, and I want to pause enough to make that clear, because otherwise the next bit will just be too confusing. So, for this graph, H primed is that red thing. Okay? Right. I lost everybody, and I don't really know, except for Mark, your co-author. I lost a lot of people, I can tell. Anyone helping with what's, is that good?
So H star is H prime, huh?
Yes, and I'm sorry for that. That's okay. So that might cause the confusion. Is that in the general induction scheme? Okay, we've got a graph H. We want to find a subgraph H primed that is smaller, has no trivial components, and reduces to H. Now, I'm giving you a particular example, and in the particular example, it's annoying that this is called H star. It's for reasons that are not very interesting. Actually, mainly because I can't edit these pictures. It doesn't really matter. So unfortunately, just H star is H primed, and that is probably what caused the confusion. I'm really sorry. Okay.
What if I put a loop on?
Oh yeah, Martin, you're one step ahead of me. That is the next slide. Thank you for that. Excellent. That is correct. So I'm showing you an easy case, and then I'm going to get to a hard case and harder cases. Okay, so so for this particular H is going to be the easiest one. And how easy it is, let's look at it. I want everybody to understand what this one is. So I have this unique vertex V star of maximum degree. I don't always have that, but here I do. Okay, so what I do is when I take an input of H star coloring, okay, I know that by induction that's hard. Okay? Now what I do is I construct this graph, and I put a vertex here and connect it to all of those guys and connect it to everything in some huge independent set. Now let's see what would happen if we took an H coloring of this thing. In an H coloring of this thing, this vertex has enormous degree. Enormous. So it will be colored V star. Because if it's not colored V star, there's not much you can do. Right? Here, this degree, 1, 2, 3, 4, 5, 6, 7, there are 7 ways I can color all of those. So if this has m vertices, I get a factor of 7 to n. That's just dwarfing everything. So in the ones that are really going to count, this is going to be colored V star. If it is colored V star, what do we have here? Oh, good, we have an H star coloring. Okay? Okay, good. All right, now, for Martin's a bit ahead of me, good. But there are lots of reasons this scheme may not work in general. For example, H star might have trivial components, so the induction won't go through, right? That's certainly possible. Or else V of H star, H star might be H. So then I'm doing induction from the same problem. That's not induction. Or there might even be multiple vertices of maximum degrees, so there might not even be such a nice thing. And all those are problems. And I just thought I'd give you some examples, and Martin already pointed out one of them, which is the next one. So here was H, but if I removed that loop from H, then the H star that I get has a trivial component. So I can't tell by induction how hard that is. Or if, I think this is what Martin was proposing, if I added a loop to that vertex, then H star would be equal to H. And then I'd be getting nowhere with the induction. And anyway, there might be multiple vertices of maximum degree anyway. So all of these are problems with pulling the scheme forward. But what I'm going to do is I'm going to talk first about this third one, because I think it's a little easier to explain. And I just want to give you a flavor of how this sort of thing goes. Okay? All right, so here's an example. And I want to give you an example where there are multiple vertices of maximum degree to show you what sort of things we could do about it. Okay, so I'm going to switch the graph H, and here's the new H I want to look at. Okay, this is just to give you a flavor of what happens. Now, what is the degree of this vertex? 1, 2, 3, 4, because the loop counts as 1. This is also degree 4, so actually every vertex in this graph has degree 4. Now, what is the graph induced by V1 here? Well, it's that. And what's the graph induced by anything else, like this vertex? Well, it looks like that. Okay, now, suppose, now it turns out to be true that both of these guys are non-trivial, they're both bis hard. So to get the kind of induction to go forward, I'd want to use the fact that these guys are hard to show that that's hard. Yeah? Okay, so what I'm going to do next is show you why that's really easy to do in the sampling world, and then talk a little bit about how you might overcome it in counting. So here's how you would solve the problem in the sampling world, and I think this gives intuition about the sort of area. So let's, well, I know that this graph H1 is bis hard, and I know that this graph H2 is bis hard. Those are just facts for my induction. And let's move to the sampling world. So let's say that, and it's true, that, well, I'm going to call this guy H1 and that guy H2, that I've got sampling reductions from sampling independent sets to sampling H1 colorings and to sampling H2 colorings, let's say. So that if I sampled an H1 coloring of a graph, if I could do that, I'd be able to sample independent sets in a bipartite graph. Equally, if I could sample H2 colorings, that would do the trick. But I want to show that if I could sample H colorings, that I'd be able to sample independent sets in a bipartite graph. Okay, so here's the cute, easy trick for the sampling world. Great. I've got an instance of this, a graph, and I want to count independent sets. Okay, what do? Well, I use the known reduction to create a graph G1 such that if I could count H1 colorings of G1, I'd be done. Also, I construct a graph G2 so that I could construct H2 colorings of G2. I'd be done. Now what do? I glue them together next to some little vertex W. And now, let's think about what happens if we sample an H coloring of this composite thing. Well, if we sample an H coloring of this composite thing, I have no idea in advance what color W is going to be. But it might be this color. And if it's this color, then what's induced here is a uniformly random H1 coloring of G1, which is just what I want. But if it's this color, that color, then that'll be there. So what's induced here is a uniformly random H2 coloring of G2. So if I look at, I don't know in advance what color W is going to be. But once I get the sample, I can look at it, and I know which side to look at to recover what I want. Okay? So that's a reduction in the sampling world, using the trick that I don't have to know in advance what goes there. Okay. And, okay. Now, here's what would happen if we did the same game in the counting world. Suppose I just wanted to count H colorings of this composite thing. So if I wanted to count H colorings of this composite thing, what would I get? Well, I might put color V1 there. So I'd get H1 colorings of G1 times H1 colorings of G2. Or there's 4 other colors that might go there. And for all those, I get H2 colorings of G1 times H2 colorings of G2. And the point I want you to take away from this is that if you know the left-hand side, it's very hard to draw conclusions about either H1 colorings or H2 colorings. So that's why sampling is easier to work in. And there may be other examples. These H colorings are the first example I've seen where the samplings are so much easier to work in. Okay? But I'll tell you, 4 minutes, I'll tell you just roughly how some nice ideas of Lovish help us to get around this problem. Is the problem clear? If we knew which one dominated, we'd be done. But it's very hard to know that in advance. Okay? All right, so we'll just... so we have to somehow choose between these, and in general there might be more than 2 possibilities. So here's the tools that are helpful from graph homomorphism. So what Lovish proved in 1967 is that if 2 graphs are not isomorphic, then there's another graph, which I'm calling J, such that the H1 colorings of J, the number of them, is different from the number of H2 colorings of J. So this is saying if there are 2 graphs, H1 and H2, that are not isomorphic, then there's some graph J so that you can distinguish between how many H1 colorings and how many H2 colorings. And it's pretty easy to just give a small extension of this, which says that if you have pairwise non-isomorphic graphs, H1 up to HT, then there's actually one of these guys that just dominates. So there's some I star in 1 up to T and J, such that the number of HI star colorings is bigger than the rest. So if I have a bunch of pairwise non-isomorphic graphs and I don't know which one I'm going to get, there exists some graph J which will dominate. Okay, so I think the last slide I'm going to show you is going to be how I would solve this example using such a J. So the little toy problem we were stuck with is we had the graph H1 and the graph H2, and we didn't really know which one would come up. So what we do is, using the theorem of Lovish, we know that there's some graph J for which one of them will be more dominant than the other. Here there are only 2, there might have been more. And what we do is we just glue a zillion copies of J on there. And now this vertex W really will be whichever one it was, H1, and now we can proceed as we did in the sampling world. Okay, so obviously there's a lot of complications, but anyway, I think what I want to do is just stop with the theorem, if that's, so if I can get back to the theorem. So it turns out to all work. Well, it'll take forever to get, there we go. But what we know then is that if you take any fixed H, it turns out this grand induction scheme kind of goes through. And if you take any fixed H, then we can do this induction. And it turns out they're all bis hard. Okay. Now, the classification program is by no means complete. And that's for two reasons. Okay? So the first is what we know is the trivial H's, we can count H colorings exactly. We know everything else is bis hard. But we don't know which ones are bis hard and which ones are sad hard. So that's an open area, and the little for loopy thing is an example that maybe live in between there. The second open problem is, look, I only classified graphs where there are no non-trivial components, and of course if you add trivial components, some of them get easy, and we have no nice theorem, so that's also still an open problem. So there's lots of work left to do, but at least we know there's nothing easier than bis. Okay, so I'm finished. Thanks.
So I guess a lot of the work in this theorem went into proving that for H you can find a subgraph, H prime, so that this is reducible to that.
Yeah,
It
all
doesn't
of
have to be
it.
a subgraph, right? Or does it?
Sorry?
It didn't have to be a subgraph. In fact,
It didn't have to be a subgraph,
so
no, that's
does
right.
it make life any easier, or you don't know? Or?
We didn't know how to do it any other way,
Any
but
other way.
yeah, there's no reason why it should be a subgraph except for that. In fact, in real truth, I mean, actually what we do is we kind of bipartize the whole thing, and so it's a subgraph of something else. But there's no reason why it should be a subgraph anyway, of course, you're right. It's just that that's what we could do.
Any other questions? Maybe again, the question was raised before. This number base, so if whether it is an intermediate problem, so there are no collapse theorems, so if
No.
there's
So-
nothing known.
Excellent. So the question was, in case would there be any nice collapses if you resolved, number bis, like if it was in P, if presable, would you get a collapse or something? No, we don't know anything like that.